Hey, what's up everybody? Welcome back to our series on Vertex Operator Algebras. Today we will be discussing the application of those contravariant forms we've been studying lately to the Heisenberg modules h hat z and h hat z plus 1/2. First, a quick review. Let G be a Lie algebra and consider the affine Lie algebra G hat, which is the centrally extended product of G with the Laurent polynomials in some formal variable t. The associated brackets involve an inner product on G, and by this point I hope these are familiar to you. Let H be an abelian Lie algebra so that the operator omega, which acts on H as multiplication by -1, is an involution, which can be extended to H hat by also taking the formal variable t 1/2 to minus itself. We can then twist the half z-graded algebra H hat by the involution, which results in a z plus 1/2 graded space, and adjoin the usual degree derivation d equals t times d by dt. We consider the commutator subalgebras of virgulia h and virgulia h of -1. We unify the notation somewhat by defining h hat sub z or h hat sub z plus 1/2. And note that both of these algebras are Heisenberg. We further simplify the notation by letting z run through either the integers or the integers shifted by 1/2. Finally, we see that as with other Heisenberg algebras, we have a module isomorphic to the symmetric algebra of the negative graded subspaces h hat z, which as usual has the form of polynomials and their derivatives in the basis vectors. Define the anti-involution omega such that c and d are invariant under omega, c being the central charge, d being the degree derivation. And the typical monomial elements of the form h times t to the n gets mapped to h times t to the minus n. We also have the linear form lambda, which here acts so that the central charge c becomes the identity operator, and the action of d, as well as any z in h, also vanishes. Now, section 18 gave us a unique bilinear on these modules, which we can now explicitly explore. The derivation d transfers from left to right without change, as would c, and as expected we see the polynomials invert upon passing them to the dual space. Note that because d acts as the degree operator, this implies that the product of two vectors, v with w, vanishes when the degree of v is different from that of w. Specializing to the case where the field is the reals, we can complexify to extend omega and lambda as before. Section 19 gave us a unique Hermitian form on these modules. Note that this effectively restricts our construction to the real form of the abelian Lie algebra H. And that's our show. Next time we'll investigate the Virasoro algebra, so get psyched.